Good morning, everybody. Thanks very much for this kind invitation in the prestigious EmTech. Thanks the chairman for the introduction. Well, usually I have a pointer, but I had off my batteries, so I had expected that there would be one here, but okay, I will explain a lot of things by hands. So, to advance the slides, I think it's this thing. Thanks very much. Okay, so this study is a collaborative effort between two CNRS and INP, Institut National Polytechnique de Toulouse laboratories, IMFT and Laplace, and it aims at contributing to greening of aircraft transport in the next 20 years. Especially this greening will be achieved by smart materials by considerably suppressing harmful instabilities as shock motion coming back and forth called buffet in cruise speed, and which can trigger flutter, which is the large wings motion. It's a structural instability which cannot be dampened, and it's very harmful when it appears. Well, it has to never appear, actually. How we will do this? Since 2006, we have a number of research projects highly steered by the foundation STAE, Toulouse, Sciences et Technologies pour l'Aéronautique et Espace, and we coordinate the platform SmartWing. You can have a look in 3W SmartWing. And within this framework, with a number of laboratories in Toulouse, we came up with smart materials embedded in morphing wings. Okay? We called this effort since years 2006 Electroactive Morphing, because the new material properties are ensured by electrodynamics, as I will explain. So the target focus is to increase the aerodynamic efficiency, to be more precise, to increase the lift, to reduce the drag, and reduce the noise. And as we go towards more electric aircraft, the priority of the aeronautics industry nowadays, is to replace progressively the hydraulic systems by electrical ones, and at the same time to go towards more light aircraft structures and more versatile loads control. Okay, in our platform, we are interested in morphing the high lift flap. We always have seen the flap, which is not deformable nowadays, but on takeoff and landing, it takes a high incidence. So now we, bio-inspired from big birds, we will give it a high deformation and at the same time a higher frequency vibration. So we will do what we called hybridized electroactive morphing in two different time scales. So, like that bird here, which knows things much better than everyone, we will use three classes of electroactive materials. The upper one is the shape memory alloys, giving high deformations and in very low frequencies, imitating the bird's action. The middle circle over there, I have not a pointer, I'm sorry, is piezoelectric materials, which will ensure higher frequency vibrations like the bird does with the smaller winglets and the feathers. And the feather action will be imitated by the third circle, which is electroactive polymers able to be at the same time highly deformable and highly frequency vibrations. So now, in my laboratory and in this multidisciplinary effort, we have morphed this A320 flap. You see on the image on the left in the turbulence structure. So we will manipulate this turbulence structure in order to achieve better aerodynamic performances. In this zoology of turbulence, you see blue vortices, red vortices, etc. We will enhance the good vortices, and we will cut off by vortex breakdown the harmful ones. How we will do this? Well, this is an overview of what happens in cruise speed with the shock wave coming back and forth and all these vortices in the trailing edge. And we will instrument the airfoil by these wires here, wires like this. Well, these wires here it is the shape memory alloys. By hitting them through Joule effect through electricity, instead of dilatate, due to the crystalline structure which will be restricted, they will restrict their length instead of dilatating. So they can ensure bending or twist of a big structure in high deformations. This is a comparison among other morphing materials to say that shape memory alloys is a good issue for large deformations. And here we will attempt to cut off all these instabilities you see here coming up through very detailed high fidelity simulations. And as time goes by, I will go directly to the effect of this piezoelectric materials, ensuring frequencies in the order from 20, 30 to 90 hertz. And you see this vortex structure behind the flap in which we do some treatment in order to enhance to cut off the coherence of these vortices and then, therefore, cut off the amplitudes of the frequency modes of these vortices. This is our prototype bending at 20% of the chord, which was presented in the Royal Society exhibition by hybridizing these wires and the piezo actuators, which is these things there, with small wires inside. And by this effect, I think I have a short time, we manipulate turbulence in order to narrow the width of the wake. The wake is this red and blue region behind the airfoil. So we see here, by the morphing, this good achievement, and at the same time, the increase of lift. So thanks, this is cruise speed which ensures by this morphing high ratio of lift over drag with improvement of over 8%. So thanks very much for your attention.